Beautiful. All right. Well, again, thank you all very much for coming. It's lovely to see you. And so, yeah, basically, we're going to wrap up FOL today. The aim is going to be to talk about evaluating FOL sentences. That is, determining when they're true and false. So the plan, I'm going to very quickly go back over the stuff we finished on, talking about sentences of FOL. This is only going to take us 5 minutes. I just want to flash up some of the definitions again to remind everybody. Then we're going to get to, and this is going to be the bulk of our time, talking about the notion of an interpretation. This is going to be our replacement for a truth table, because unfortunately we cannot do valuations for FOL. Valuations have to do with ascribing truth values to atomic sentences, and those are gone, unfortunately. Those are only around in TFL. Instead, we're going to talk about, just to spoil it, extensions of predicates. And that's going to be our sort of surrogate for truth values for atoms. Then once we have that, we'll talk about truth in FOL. So thinking about when certain sentences are true and false according to an interpretation. And then finally, we'll finish off by defining up a bunch of semantic notions. These are going to be structurally similar to, but different from, the semantic notions we defined for TFL. And the key difference is that the ones for TFL were all defined in terms of valuations, right? But we're not going to have those here. Instead, we're going to have everything defined in terms of in an interpretation. So that's the plan. I know it's exciting. I'm excited. Okay, cool. So again, quick review about sentences for FOL. First thing is our language, again, has basically 6 constituent types of parts. You have 2 different kinds of terms. You have predicates, connectives, brackets, quantifiers. And we can say that an expression of FOL is any concatenation of these, right? Any kind of ordering of them you want. But expressions aren't sentences. To get to how we can define an FOL sentence, we have to go via the notion of a formula. So we'll say that a formula is any sentence or any expression that can be turned into a sentence by adding a quantifier in the front. And we know what a term is. A term is any name or variable. And we can define a notion of an atomic formula. An atomic formula, so this is the fancy way, but we can put it even simpler. If you have an n-place predicate, the predicate plus n terms gives you an atomic formula. Similarly, any identity statement with 2 terms on either side of the identity predicate is an atomic formula, and nothing else gets in the door. Okay, so atomic formula are effectively our basic unit, right? This is our replacement for atomic sentences. But note, atomic formula need not be sentences quite yet. And then this is basically just the rules that tell us how we can use our connectives, and importantly, also how we can add quantifiers. Effectively, clauses 7 and 8 tell us, right, if your formula has a variable that's free, that is, there isn't already a variable bound to some quantifier, there's a quantifier kind of attached to an occurrence of a variable, you can stick a quantifier in the front and you're good. You haven't violated the construction rules. So, and notably, I just use these terms, but we can define them. We can say a bound variable is an occurrence of a variable within the scope of an associated quantifier. And a free one, well, it's just not bound. There's no quantifier that's attached to it. And then finally, a sentence of FOL is any formula that doesn't have any free variables. So that's the kind of middleman, right? We have to go via this notion of formulas, and then we can say, cool, a sentence is any one of these, any formula that doesn't have a free variable. Either because all the variables are bound, or it only has names. Cool. Okay. And again, the big thing here, to go back, the big thing here is that we have a definition, a rule set for building complex formulas. And don't worry, I know this is in the blue, but I'm not going to ask you to write this down. I'm not that much of a monster. Right? Conveniently looking right at the camera as I said that, right? Okay, so that's really, again, just to review, right? We have the basic sentential structure. We know how to build FOL sentences. We've been working on this for the last couple weeks. So let's talk about when they're true and when they're false. So FOL sentences are split up into predicates, terms, and quantifier expressions. Right? And this is really useful. In fact, this is the big step in expressive power for this language. This lets us consider what's true or what's the case for some particular object, if we're using names, or for some or all or none or not all of the things in the domain, if we're using quantifiers. Now, when we interpret FOL sentences, we're considering what the predicates are true of. This is going to be our big idea, right? We're going to settle, hey, what are the predicates true of? The predicates being true of or not being true of certain things are going to then tell us, hey, here's what our atomic formula's truth values are, and then that will tell us what the connective's truth values are, just like it did in TFL, and so on and so on and so on upwards until we hit the main logical operator. In order to figure out what the predicates are true of, we need to talk about the extension of a predicate. That is the collection of objects that satisfy a predicate, right? This is why we talk about FOL being an extensional language. Notably, have people come across this notion before? Have we come across the idea of extensional? Okay, we'll talk about it probably more in a bit. Right? So the key for FOL is the extensions of predicates. And in fact, that's really what interpretations are. Interpretations tell us a domain and the extensions of predicates. And they'll also maybe tell us something about names if they're associated. So when we have a predicate, D, right? Well, we can actually talk about or settle the extension of this predicate in two different ways. One way that we've been doing it has been indirectly. You settle the extension of a predicate indirectly by describing some property or quality or way of being, and then you go out in the world and you figure out what satisfies that property or way of being. Right? So D is a dog that lives with Nathan. Cool, so what you have to do then is go out, look in your domain, and see what things in the world are dogs that live with Nathan. Right? Another one, right, is a spy. Right? If we indirectly stipulate the extension of predicate S by saying, cool, it's the collection of things that are spies, well, what we have to do then is go round up all the things in our domain that happen to have that property. So that's one way to settle the extension. But another way to settle the extension is to just do it directly. And we directly settle the extension. You just simply list the things that have or satisfy the predicate. Right? So instead of saying, okay, here's the property and let's go find out, we just say, here are the things. It's Mira, and that's it. Or here are the spies. It's Haftor and Igmar, and nobody else. So when we think about the extensions of predicates, you can do it either way. Indirectly, where you specify a quality and then you go and look, or directly, where you just simply list, these are the ones that I want to count. It's notable that we have been talking about predicates as if they express real properties, but they don't have to. Predicates are just predicates. They're arbitrary. We can make them whatever we want them to be. That is, predicate extensions can be settled however we like when we're building interpretations. To put it another way, logic doesn't really care about what we think naturally goes together. To logic, all collections of objects or all different ways of being are on equally good footing. It's properly egalitarian. Amen. So that is, a predicate like is a man or a mountain is just as good for us as is a cow. We don't really care, right? They're just predicates. They're just more stuff for our machinery. All we care about is what are the things that are in the extension. So let's kind of get a grip on this by thinking about some sample predicates, right? Suppose we're talking about the universal domain, right? Well, I'm going to introduce the predicate Z or Z, whichever, if you're feeling Canadian or British or American, right? Z is true. I'm going to directly stipulate the extension. Say Z is true of all and only the following: me, the Eiffel Tower, and everyone who's ever lived in Tilburg. So again, we're just sort of stipulating the extension of the predicate. This is the thing we do when we're building interpretations. And if we add some names, we have little n for me and little d for Darth Vader, right? So based on this, if we say ZD, right, is Vader in the extension of the predicate? No, right? He ain't me, as far as I know. He's not the Eiffel Tower, and I'm pretty sure Darth Vader has never lived in Tilburg. How about Zn? Is n in the extension of the predicate? Yeah, cool. We have already got how to make these atomic formula true. You look to see, is the thing named in the extension of the associated predicate? If it is, it's true. If it's not, it's false. Yes? So that could be, but remember, when we're building an interpretation, we might want to build this weird, very, very weird extension. Extensions are arbitrary. We can make them however we want. So there's going to be different predicates that'll have the extension of like being me, being the Eiffel Tower, being someone who's lived in Tilburg, but I'm interested in the extension of this one, of Z right now, and I've stipulated it's this. That's the cool thing. To go back a slide, when we're doing extensions, when we're fixing extensions, you can go out and look, or you can just say it's these things. And importantly, that is the power when building interpretations. You can make the extensions be whatever you want. This is the replacement for just simply assigning truth values to atomic sentences. We assign extensions to predicates. So again, right, Zn, based on that extension we just talked about, Zn is true because I'm in the predicate's extension, and Zd is false because Vader is not in the predicate's extension. Notably, Zx is not true or false. It doesn't say anything yet. This is not a sentence. To make it a sentence, we have to bind it with a quantifier. So if we stick a universal in front, it says, hey, everything in the domain is in the predicate Z's extension. Right? That's what for all x, Zx would say. Everything in the domain is in the extension of Z. Similarly, the existential tells us there's at least one thing in the domain that's in the extension of Z. So based on that, to go back, right, given this setup, is for all x, Zx going to be true? No, I mean, there's a whole bunch of things that aren't in the extension of Z, right? Darth Vader, for example, is one. But is the existential x, Zx true? Is there something in the extension of Z in this interpretation? Yeah, I mean, me, all of you, anyone, if any of you who live in Tilburg, you're in the extension, right? There's a whole mess of things in the domain. Again, this is the kind of basic idea. It's going to just be building from this. So we can say that a one-place predicate descriptions, they're true if and only if the object denoted is in the extension of the predicate, and they're false if the object isn't. Two-place predicates require that we specify order. Right? So we could have is friends with, right? A two-place predicate where one is friends with two. And we can do the exact same thing. We can indirectly stipulate the extension here. That is, we go out, we look in the domain and see what pairs satisfy it, right? Or we can directly stipulate the extension. And when we directly stipulate the extension of a two-place relation, you don't just list names. You have to list them in the order they fill the gap. So for example, I could specify the ordered pair Nathan-Mira. That is, Nathan is friends with Mira. And I could specify Amanda-Mira. That is, Amanda's friends with Mira. But note, the order we specify them tells you the order that they fill the associated gaps. So on this direct stipulated extension, if we have N be me, M be Amanda, M be Mira, and A be Amanda, FNM and FAM are true. These ordered pairs are in the extension, but FMN and FMA are false because we don't have the pair the other direction. Mira is not friends with us, even though we're friends with her because she's grumpy. Right? That's basically the idea. So, when we're giving the extension of a one-place predicate, you just list names. List the things that are in the extension. If you're giving the extension of a two-place predicate, ordered pairs, and importantly, the order that you write them down tells you the order that they satisfy the predicate. So, maybe to kind of extend on this, right? How about FMN? Is that going to be true or false on this extension? FMN. Right? Say again? FMN. No, right? We don't have the ordered pair Mira, Nathan. How about FAN? That's not there either, right? We don't have the ordered pair Amanda, Nathan. Yeah.
Is it irrelevant then that these are like ontologically true?
Does not matter.
Okay.
When we're doing extensions, we don't care about what's really the case. We are building an interpretation, a model situation, and thinking about that. This is why it's entirely arbitrary. Right? We can make the extension whatever we want it to be. So here's the reasoning behind that. It's a nice kind of segue here. The reasoning behind it. When we're thinking about FOL sentences, we want to think about all of the possible situations that they could be describing. And instead of thinking about, okay, we're going to flip these atomic parts on or off, we have to think about, well, what could the predicates be? Or to put more bluntly, what could the predicates be true of? That's really what we're doing here. We're thinking about, hey, what are the possible different extensions these predicates could have? And once we fix these extensions, what does that then do to the associated FOL sentences? We don't care about what they actually apply to, anything like that, when we're doing evaluations for FOL. Okay, cool. One thing to note, identity, unsurprisingly, is a special two-place predicate. The identity, the interpretation of identity is fixed. You never tell us what it is, right? It's just simply going to be given if and only if the two things named are the same object. Right? So this isn't something that you tell us the extension of because identity is special. It just works in a special kind of way. There's no messing around with it. So again, one-place predicates, we just list them, list the objects in the extension. Two-place predicates, we give these angle brackets to tell us, okay, this is an ordered pair, and then you tell me who's in slot 1, who's in slot 2. Nice. So we can then formalize all of this, define our notion of an interpretation. We can say an interpretation consists of three things: a specification of a domain, so the collection of objects that we're going to be considering, an assignment of exactly one object within the domain for each name that we care to consider, if there are any names, and for each predicate that we're considering, a specification of what things, and if it's relation, in what order, the predicate is true of. Or to put it another way, every interpretation is going to tell us, here's the domain, here are what things in the domain our names pick out, and here are the extensions of the predicates that we're interested in. The important thing that an interpretation does is this: it fixes the extensions of the predicates. And by fixing the extensions of the predicates, it's going to tell us what the atomic formula's truth values are. And those in turn are going to tell us what the connectives do and how the quantifiers work and everything else. It's all going to stem from fixing those extensions. In this way, we're going to indirectly settle truth values of FOL sentences by settling extensions of predicates. Does the kind of idea make sense? Does the basic thought process, right? Have people done like set theory stuff before? This is very similar to we fix the kind of base sets and then we can start performing operations on them. It's the same idea. We're fixing the base sets here, the extensions of our fundamental predicates, and then the rest is just Boolean operations on top. But we're very carefully avoiding set theoretic talk. Cool. So this is what an interpretation is. And to then say when FOL sentences are true and false, we will say they're true or false relative to an interpretation. Here's a sample. Yes, sorry.
So we always use direct relations.
Good. So importantly, you can do either. One thing that's very easy is you could say, right, my domain is people in this class, and I'll have the predicate P applied to anything that's a person. So that's easier than listing every single name, right? You can also, if you have a very small domain, just list all the objects. Right? You're always free to go back. You can do either. You can do either when you're building. Sometimes it's very helpful to do it indirectly. Often it's going to be easier to do it directly. Right? These are the things that are in this predicate. But if you have, 180 things in your domain, you don't want to do that. Right? Okay, good question. Cool. We're going to come back to kind of what's the plan or how to build interpretations, right? We want to get this basic idea through first. So here's a simple interpretation. Right? It looks an awful lot like things we've seen already. Right? So our domain can be universal. We can have the predicate D be is a dog. That's the extension fixed indirectly. We could have F be the predicate is friendly, again, fixing indirectly. We can have the predicate Z, which is fixed directly. This is the one I stipulated earlier. And I can have the predicate A, which applies to Darth Vader and Mira. Right? They're grumpy. Or maybe A here is aggressive. That would work for my dog, the murder machine. Right? And then we have, in this case, just three names: little n, little d, and little m. Right? Now, there's a whole bunch of other things in the domain that we don't have names for, but that's okay. We just don't need them. So this highlights, again, actually addresses your question, right? When we're setting the extensions here, you can do it either way. Fix it indirectly or directly, depending on what you want to do. Importantly, you can do whatever you want in terms of picking a domain and picking extensions. We're going to talk more about how to build these, but that's a thing to keep in mind, right? There's no kind of restriction to what's actually the case. Let your imagination go wild, right? So, another neat thing is that as well as building interpretations like we just did, you can also build them diagrammatically. This is very handy if the only thing you're dealing with are two-place relations. So if we have R be a two-place predicate, right? Well, then we can just express it as an arrow, right? You draw some dots. The dots are the things in the domain. And then we can show that the relation holds by drawing a pointed arrow, right? So in this diagrammatic interpretation, RCA is true. That is, there's an arrow that starts at C and goes to A. But RAC is false, because there is no arrow that starts at A and points to C. So again, diagrammatic interpretations are another way to express the exact same thing to build an interpretation. It shows us the domain by just simply, hey, the dots on the page are the domain. We label them. Right? And then we can show the extension by how we draw the arrows. This is, again, basically another way to directly stipulate the extension of a relational predicate. Cool. Okay. So this is the basic idea of an interpretation. Right? It tells us a domain. It tells us any names that we want to know or that we're concerned with, and it fixes the extensions of the relevant predicates. Right? And armed with interpretations, we can now start to evaluate FOL sentences. That is, know when they're going to be true and when they're false, according to given interpretations. Before we press on, pause. Questions for me so far? Is it the basic idea kind of clicking? Yeah, please.
So, on the example, I think this slide's left.
Yep.
You have Z and A. I don't really see how those are like predicates.
Good. So importantly here, right, what we're thinking of is we could just describe this as a kind of is one of these things. And then here's the list of things. That'd be one way to kind of pick out the predicate. From FOL's perspective, all a predicate is the things it applies to. The meaning of a predicate for FOL is just its extension. So saying D means is a dog, and saying D is let me list every dog that ever was, and ever will be, and ever and is. From FOL's perspective, that is the same answer. Similarly for this, right? I think this pointer's dead, right? Similarly for the predicate Z, right? I've given the extension to you, but we could also describe it as, I don't know, is Nathan the Eiffel Tower or lives in Tilburg? It's not a very interesting or natural predicate. From our perspective, it's just as good. All that matters is that we know the extension. So again, the way we've been talking about FOL predicates has been almost always in terms of like this, in terms of what's its English meaning, but that's to get us into the idea. Once we're actually really building interpretations, we don't care about the English meaning, we just care about what's the extension. Yes? It's just something we decided to stick in the extension.
So where is the extension?
Good. So when we write our interpretation, right, we can write it like this. So we've got our domain, and then we're listing our predicates and their extensions. The predicate extension for D is whatever in the domain satisfies the English predicate is a dog. So this is going to be another way we could write this is a list of every dog that has ever existed, exists, or will ever exist. That is the extension. And then for Z and for A, instead of giving you an English predicate, right, and is blah, 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 I've just simply listed the things that are in the domain that satisfy the predicate Z, right? It's Z.
No, but like, for example, D, it's like, is a dog.
Yeah.
So Z is, does that include Nathan and Michael?
Z is the list, this list of things. Z from FOL's perspective, again, the meaning of a predicate is just whatever it applies to.
Okay, so how would you use that in the plural? Like, how would you?
The same way we did before, right? So we'd start saying like, Zn, is Zn true on this interpretation?
Oh, because Nathan is
Is in the extension, right? Is Dn true? Yeah, thank you. I'm not in the extension of the predicate is a dog. Note, here's the important thing to see the difference. Over here, this bit is in English. So we're saying, okay, cool, the predicate D, this bit of FOL, the extension of this predicate is going to be satisfied by the things that satisfy the English predicate. We're using English to help ourselves out. But the important thing, all that an FOL predicate means for FOL is just a list of things that make it happy. Right? So again, this is the kind of important idea. The meaning of an FOL predicate is its extension. Yeah.
So if I use set in a sentence, if I use set n, that would just be Nathan.
It says Nathan is a Z, right? What's the English equivalent to being a Z? I don't know. I don't really care. We're just talking in FOL at the moment, right? So the thing to remember with all of this too is we're building these interpretations, building these models for particular purposes. We're going to talk about what we can use them for in a few minutes. But this is just the kind of thing we can do. Extensions are arbitrary. Make them what you want. Yeah.
As you said earlier, this is all just kind of set theory, right?
It is.
This is part of that set. This is part of that set.
Yes. That's basically all we're doing with these is we're saying here are the members of the various sets.
Yeah.
And the meaning of a predicate is just the set, the collection of things that satisfy it. That's it. That's all a predicate is for FOL. It's so importantly, one of the things that, again, can be a little bit confusing in this transition is the way we've been doing it up till now. We've always treated FOL predicates as if they are FOL expressions of English, right? We talked about like the predicate S, it means is a spy. Well, that was us trying to get you into the door, right? Now we got to kind of let go of that idea, right? This is a way to help you figure out what the extension of the predicate is. But what it really means, what the predicate S really means is these things. The things that make the predicate true. Yeah.
How do you differentiate between like the English and FOL? Like in English, like for example, for D and F, like it says like is a dog or like is friendly. So you can say like, so like if you put something in there like, to say whether it's true or not, you have to like look at like whether it fits within the English, right? But then as for Z and A, then you're just like looking whether it corresponds with what's inside the set.
That's it.
Yeah, but then like for D and F, like how do you know like whether that thing is friendly?
So you have to, in this case, yeah, to assess that, say, FM is true or false, you need to go out in the world and see if the thing named by Mira, in fact, has the property of being friendly, right? This is one of the reasons why it's sometimes useful to set things indirectly and sometimes not. Because you've got to go get your hands dirty and actually see, does this object satisfy the English predicate, right? It's helpful, so the indirect stuff is helpful when you know, basically, but listing everything would just be a hassle, right? Like again, if we have the domain be people in this class, and then I wanted the predicate is a person, I don't want to list everybody's name, right? I just use in this class, right? Or is a person. That's the kind of move we would make there. Right? Okay, yes?
Would it be wrong to say that Z is like a subdomain?
You can talk about it this way. In fact, you can always think of the extensions of predicates as subdomains. Notably, one of the things that our rule set doesn't strictly require is that the extensions of predicates are restricted to stuff in the domain. Though talking about the things that are in the extension that aren't in the domain is never going to be very helpful. Right? So if you find that helpful, sure, that's totally fine. But again, another way to think about it, just the extension of the predicate, the collection of things that satisfy it. Right? Here's the things that are Z's. Here's the things that are F's. Here's the things that are A's. That's all the meaning of these predicates are. Okay. Cool. Yes?
So if we have the domain of mammals, then wait, how would I say that? If we have the domain of humans, then AM wouldn't be true anymore.
Yeah. Yeah, AM wouldn't be true. In fact, M could not name Mira, right? We would have a problem with this interpretation because we would have a name that doesn't pick out something that's in the domain, so it would be empty. That would be right? So we couldn't have that. Right? Okay. So let's kind of take this idea. I think some of these will also work themselves out when we start thinking about how to use interpretations. So let's press on to thinking about truth and FOL. Right? So there's three kinds of FOL sentences. There's atomic sentences, right, which are just going to be a predicate with the appropriate number of names. There'll be sentences whose main operator are connectives, right, and or not the conditional or the biconditional, and sentences whose main operator are the quantifiers. We're going to provide an account of truth for all three. And it's always going to be true according to an interpretation or in an interpretation. You'll also sometimes see this as truth in a model. Right? So atomic sentences, I'm going to give you the scary version and then I'll just explain it in simpler terms. Right? When R is an n-place predicate and A1 through AN are names, R A1 through AN is true in an interpretation if and only if R is true of the objects named by A1 through AN in that interpretation. Considered in that order if it's a relation. Right? And then an identity statement's true if the two terms name the same object. So, what's the simpler explanation? Put really bluntly, right? Zn is true if and only if on the interpretation the thing named by n is in the extension of Z. Zm is false if and only if the thing named by m is not in the extension of Z. We did this a minute ago, right? Remember, we're talking about Zn and Zd, right? About Mira being friends with Amanda versus Amanda being friends with Mira. This is the same idea, just expressed in much, much more buildy language, right? So, a predicate with the appropriate number of names is true if and only if the names are in the extension of the predicate. That's easy. So you can even see it here, right? We can do this either in a diagrammatic way or with some written down version, right? Again, looking at this one, RAD is true on this interpretation because there's an arrow that starts at A and goes to D. Right? RDA is true because there's an arrow that starts at D and goes to A. But RAC is not true. It's false because there's no arrow that starts at A and goes to C. Again, very straightforward. Similarly, if we want to use this written out interpretation, right? Zn is true, Zd is false because the thing named by n is in the extension of this predicate. The thing named by d is not. That is the simplest one, right? An atomic sentence of FOL is true in an interpretation if and only if the thing named is in the extension of the relevant predicate. Cool? So there's our first one. Now, that's where it's just an atomic sentence. The next one is, what about connectives? Right? Again, I'm going to give you the scary one, but actually it's very simple, right? The connectives work exactly like you think they would. The negation is true if the negated sentence is false. The conjunction is true if and only if both conjuncts are true. The disjunct is true if at least one disjunct is true. It works just like it did in TFL, guys. It's exactly the same as in TFL. Right? The connectives work exactly the same. So that's nice. That's easy, right? The first two are very easy, right? If it's an atomic one, you just look to see, is the thing named in the extension? If it's a connective, well, cool. You just figure out the truth value of the parts, and that will tell you, using the same things we did with truth tables before. So all that's left, yes?
Small question. If we're defining, let's say, A is equal to B or A is not equal to B.
Mhm.
So for not equal to, do we say A is equal to not B?
No, never, ever, 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 never. So importantly, negation always attaches to a complete formula. Right? It never attaches to a term. So it feels like it might because the equal sign and the negation look like the negative sign in like algebra and things like this, but negation is not the same. Right? You can attach negation to A equals B, and that tells you the identity claim does not hold. That is what you would say. Right? So yeah, good. That's an important syntactical point. Right? It looks like the negative sign, but it's not. It's negation. It's our special symbol. It works in a special way. Cool. Okay, so we got the atoms, we got the connectives, no problem. All we got now is the quantifiers. Actually, it's going to be very easy. It's going to look horrifying, but the basic idea is very simple. Okay. So I'm going to talk you through the basic idea. Oh, sorry. First, some practice. I forgot about this. I apologize. So let's do some quick practice to see if these sentences are true or false on the interpretation. So here's my selected interpretation. Our domain is all Simpsons characters. We have the predicate is American, is a baby. The two-place predicate is older than, little m for Maggie, little h for Homer. Right? So we've indirectly settled the extension of all of these predicates. So how about on this interpretation, is our first sentence true or false? Okay. Right? So if we look at the sentence inside the negation, it says Maggie's older than Homer. Right? On this interpretation, it tells us Maggie stands in the is older than relation to Homer, which is false, right? But then if it's false, that means the negation's true. So this sentence is true on this interpretation. Get it so far? Yeah. How about our second one? BM and OHM. Is this true or false on our interpretation? It's true, right? So the conjunction is the main operator. The conjunction is going to be true on the interpretation if both conjuncts are true. And BM, Maggie's a baby, cool, right? And OHM, Homer is older than Maggie, cool. Both conjuncts true, conjunction happy. How about this one? A little more complicated. OHM, if and only if, not AM. Well, what's the main operator here? It's the if and only if, right? It's the biconditional, right? It's the biconditional. So the biconditional is true if and only if, haha. Both sides have the same truth value. So if we look on our right-hand side, right? Not AM, is not AM true or false? Well, Maggie is an American, right? So it's false. Right? The negation is false. And is Maggie older than Homer? Right? Maggie is younger than Homer. That's okay. It's okay. right? So both sides have the same truth value, so that means the biconditional's true. Do we see how we're doing the same thing that we did with TFL before? Right? Yes.
I understand that like connect is the same as TFL, but how do I know if something is true or false by itself? Like
Good.
let's say P plus O and H is the first one without the negation. How do I know that it's false?
Good.
Are we talking about validity or sum?
Neither of those things. We're just talking about the truth or falsity of a given sentence, right? So what we do is you look at the interpretation. Use this, right? So OMH is going to be true. So let's just ignore the negation for a second. OMH is going to be true if and only if the thing named by M is older than the thing named by H. And M is Maggie Simpson, and H is Homer. So, do we think that Maggie stands in the is older than relation to Homer?
So we're talking about facts here.
We're being governed by whatever's the case in the interpretation, right? So, because we've indirectly stipulated the extensions of these predicates, we have to go look and see, right? We have to find out, hey, do the things specified in this order stand in the is older than relation, right? Is Maggie older than Homer? No, she's a baby. He's her dad. He's got to be older. Right? So in this case, because we've indirectly stipulated, we have to go see what are the listed extensions of these things. Right? Does that help? Yes.
Do we only get examples of the ritual that discussed in the lecture? Because I didn't know Maggie was a baby.
That's okay. This is just picking out a range that I figured most people would know. No. This is, again, I'm picking something that I kind of hoped. Do people not know The Simpsons? I mean, I know it's really taken a dive. People vaguely familiar with The Simpsons universe. So that's fair. But importantly, even if you don't know the particular thing, we're just using the example to kind of get a feeling for how this works, right? So what's important is, given that Maggie is in fact a baby, right, then it's very simple to follow what happens. Yeah?
Is the extension of predicate all sets of two possible Simpsons characters where one is older than the other?
Yes, right? So again, remember, the extension of a two-place predicate is an ordered pair, right? It's an ordered pair. So every character who's older than some other character, you're going to get that ordered pair.
So you could say the extension of that is the collection of the sets which satisfy that, right?
Yes, the two-place sets that satisfy this. Yes.
So in the exam, are you going to give us what culture references or?
No. This is something, I mean, honestly, I'm so surprised that people don't know The Simpsons. Come on. No, we'll come up with better ones then. No. This is, again, I was hoping that this might be the sort of thing that people would be able to digest. But yeah, that's fine. Okay. So again, with the basic thought, this is the thing I want to get through here, right? When we think about things like OHM, that's going to be true on an interpretation if the ordered pair HM satisfies the predicate, right? And then the connectives are going to be true or false exactly like they did with TFL. Okay? That's the important thing. Now, let's talk about the quantifiers. The quantifiers are slightly weird. And I want to start off by actually just thinking about it intuitively, right? And then we'll go through step by step to talk about how they actually get evaluated, right? So let's think about this intuitively. And apologies if you don't know the deep Simpson lore, right? Right? So let's start off with our first one, right? If we're thinking about this quantified sentence on this interpretation, right? First thing we can ask ourselves is, what does this first sentence say? Yeah, there's some Simpsons character older than Homer, right? There is some Simpsons character, there's something in the domain that stands in the O relation to H. Okay. Intuitively, is that true? We've got Grandpa Simpson. We've got Mr. Burns, who we'll come back to Mr. Burns in a minute, right? We've got the Mole Man, who's also an old man, right? There's lots of characters who are older than Homer. Cool. So that one should come out true, right? How about our second sentence? What's our second sentence say? It's a little more complicated. Right?
There's someone that's older than Maggie, and there's someone that's not American.
And that person,
That person's
right?
not American.
Yeah, there's some non-American who's older than Maggie. And as I said, well, right, they're in the domain, so they've got to be a Simpsons character. So can we think of anybody? I know. Does anybody who knows the Simpsons, can anybody think of anybody?
What's the name of the guy that owns the Pizza Mart?
Apu?
Yeah, that one.
He would be one, right? Though actually, as it turns out, I think in the deep lore, he's been faking the accent for years and years and years. Yeah, this was a big thing a couple years ago. Groundskeeper Willie is one. He's Scottish, famously, right? There's the Mexican bumblebee guy. That's another one, right? There's a bunch. All that matters is there's at least one, right? So again, this should come out true, right? How about our third one? Yeah,
that's a tautology, so of course.
cool. What does it say?
It says every Simpsons character is either American or not American.
Everybody's either American or not American, right? So if we pick anybody, like one of the weird aliens, right, they're not Americans, so cool, right? If we pick any of the Simpsons, they're Americans, so cool. No matter who we pick, it looks like this sentence is going to be true, right? Regardless of who we pick. So true, true, true. So far, so good. Now our fourth sentence. What does it say? Maybe we can help ourselves. What's our fourth sentence say? Yeah?
For every person, there's someone that's older than that person.
Yeah, for every person, there's somebody who's older than them, right? Now, intuitively, is this going to be true? Why not?
Because there's someone who must be the oldest person.
Someone who might be the oldest, right? If there's anyone who's the oldest, we can plug them in for our X, and then there is not going to be anyone we can find that can be the Z. So it's going to be false. Now, importantly, if you get the thought process that we just went through, then you know how to read these sentences, right? All you do with the existential is you think, is there something in the domain that I can fill in for X that's going to make the sentence true? If there is, the existential's true. If there is not, the existential's false. Similarly, for the universal, it's going to be true if and only if it doesn't matter who you pick. If you can fill them in for X and the sentence comes out true, it's true. But if there's even one that you fill in that makes it false, the universal's false. That's the basic thought. Now, I'm going to go through this in slightly more detail because it's helpful to have the actual full-blown story here, but that's the basic idea. Did you have a question?
Yeah, so isn't it, can be accents as be the same person?
Sure.
It's false as well.
Well, in that case, it doesn't necessarily show us that it is false, right? Because what we do is, this tells us, hey, no matter who you pick, there's bound to be something in the domain that's older. So you could pick the same thing, but that's not going to show that it's false. We need to show that no matter how hard we looked, we can't find the Z that does the job. So again, this is the important idea. If we get this thought, you're good. Right? Now I'm going to spend the next 5 minutes telling you the slightly more detailed version of it. Right? The slightly more detailed version here is basically that we can always extend our interpretation. So importantly, you'll note that our interpretation does not include names for all of the Simpsons characters, which is good, because if it did, this would be a really, really annoying slide, right? Because there's billions of these fuckers, right? So we don't have a name for every character, but importantly, we could have, right? We could, for any given character, extend our interpretation and add a name for them. And this is the idea we're going to use to help us figure out how to interpret quantifiers, by extending our interpretation in various ways. So for our existential, right, what we do with the existential is we ask, hey, is there a way that we could extend our interpretation? That is there some name we could bolt on that already names something in our domain that we could then fill in? So again, this is just the roundabout way of saying the same thing we said before. Right? We know that there's some stuff in the domain that we don't have names for, but we could name it. That is, we can extend our interpretation by adding a name for it. So we do it, right? Add a name. Let's add a name, little b, for Mr. Burns. Right? If we had little b for Mr. Burns, well, we could slot him in place of x, and we would get OBH, which is true. Burns is older than Homer. So this gives us a way to know when the existential's true. An existential will be true if and only if there's some extension of our interpretation that when we extend it by adding a name for something in the domain, the replacement turns out true. So that's how to treat the existential. There's some extension that works. Right? And note the same thing with a more complicated existential, right? Doesn't matter. There's some extension for our interpretation that gives us a name that we can plug in place of the variable, and that when we plug it in, that sentence is true. The universal is slightly more entertaining. Right? It's the same idea. We have an extension, but this time we add a new name, and we don't say who it stands for. In our extension, our name kind of stands for anyone or everyone. That is, we play a little dirty semantic trick here, and we basically have A as a dummy. It can be Homer, Maggie, Burns, the Bumblebee Man, Apu, anybody, doesn't matter, right? No matter who A names, if we can slot it in place of X, and the sentence comes out true, no matter who it names, then the universal is true. But if it matters who it names, that is, some of them will make it true and some of them will make it false, then the universal's false. Again, this is just the more technical machinery version of the same thing we talked about before. And our last one where we have iterated quantifiers. Right? The process is the same. Right? The process is the same. We take our interpretation and we treat the quantifiers in the order that they appear. Right? And remember, we wanted this one to come out false because there could be the oldest character. So we extend our interpretation by introducing the name A, and we have that name pick out whoever the oldest character is. Now, in previous years, we've had debates. I think it's Burns, because there's an episode where he's shown being old when the dinosaurs are walking around. So I think he's the oldest by far. But yeah, I'm happy to grant that. Whoever that person is, the oldest Simpsons character, we'll call them A. Right? Well, since that person is the oldest, we cannot further extend our interpretation by adding a name B such that OBA is going to be true. No matter how hard we dig around in this domain, and remember, there's like billions of these characters. No matter how hard we look, we can't find some B that's older than the thing that we've named as A. And that's why this existential's false. There is nothing that's older than A. And because there's at least one thing for which there's nothing older than, well, then our universal is also false. Again, the basic process here, I hope, is clear. Right? Doesn't matter if we've got them iterated. All we do is we just treat them one at a time. We do an extension, right? And if it's a universal, then the name that we're offering as the extended thing can stand for anybody. And if it's an existential, then we want to find at least one thing. Okay, cool. So here's the slightly fancier, oh, did I skip? Yeah. Here's the slightly fancier technical description of this, right? If A is a formula containing at least one instance of variable X, and X is free in A, and C is a name, then we can substitute the name in place of the associated variable, right? And get what we'll call substitution instances, right? Again, don't stress, this is just to be very explicit about how the machinery works, right? And we can say that this universally quantified sentence is true in an interpretation if and only if the substitution instance is true in every extended interpretation, assigning an object to any name C. Right? That is, it doesn't matter who C names, it's always going to be true. And similarly, the existential is true if there is some extended interpretation where C names an object that was already in the domain. Again, these are the same ideas we talked through just a few minutes ago. It's hopefully reasonably clear, right? Okay. So we figured it out, right? Now we know how to tell when an FOL sentence is true in an interpretation. If it's an atom, just look to see if the named things are in the extension of the predicate. If it's a connective, you know how to do connectives. They work just like they did in TFL. If it's a quantifier, we look to see if it's an existential, is there some extension? Cool. Or if it's a universal, is every extension? Cool. Otherwise, they're false. That's it. That's really it. The rest is all just kind of gravy. So, this is how we do truth in FOL. Now, once we have truth in FOL, we can use this idea of true in an interpretation to define up a bunch of semantic notions. That is, we can use interpretations to look for things, right? And remember all the semantic properties we defined for TFL using tables, right? So like there was being a tautology, being a contradiction, all of this stuff. Going to have the exact same stuff. Just instead of being defined in terms of valuations, they'll be defined in terms of interpretations. Right? So let's go through them. We're going to go through them quick. So we've defined truth in FOL. We can make sense of a number of semantic notions. These are very similar to the ones we did for TFL, but importantly, again, everything in TFL, the magic word was valuation. Everything for FOL, the magic word is interpretation. We're going to use the same symbol, again, our double turn style, to express entailment. In this case, we'll call it logical entailment, because just between friends, FOL is what many people mean when they say formal logic. So we're going to use this double turn style to say logical entailment, and it's going to be defined in a very similar way to what we did before. That is, we will say some sentences A1 through AN logically entail C, if and only if there's no interpretation in which A1 through AN are true and C is false. Right? Again, that should be really familiar, right? Because that was the same thing that we had before, just instead of interpretation, it was valuation. For TFL, we called it tautological entailment. For FOL, we call it logical entailment. Right? So again, this relation holds if and only if there's no interpretation that makes the stuff to the left true and the thing to the right false. Hey, cool, here's something else, right? We can have an argument in FOL with some premises and then a conclusion. And that argument's going to be valid if and only if there's no interpretation where the premises are all true and the conclusion's false. Yay! Fucking awesome, right? Again, another beautiful, even more powerful tool than what we had before to test for validity. Now we have an explicit way to do it. Can you build me an interpretation that makes the premises true and the conclusion false? Similarly, the argument's going to be invalid if there's even one interpretation where premises are true and conclusions false. Or to put it another way, right? If there's some way to ascribe the extensions of the relevant predicates that makes the premises true and leaves the conclusion false, then the argument is invalid. Yeah.
Is there a difference between the logical entailment and saying follows from?
It is basically the same notion, right? So the one thing is this is defined explicitly in terms of interpretations. So we have an underlying tool to tell us when the double turnstile, when logical entailment holds or doesn't hold. Right?
The first two boxes basically say the same, no?
They do, right? So again, this notion of validity, right, is basically our FOL version of validity, right? Just like how we had, right, you could test an argument for validity in TFL. If tautological entailment held, you can test if the arguments expressed in FOL, is this argument valid, by just looking for this. It's the same thing. Okay, so this is the first big payout of interpretations, right? We can test for validity by constructing interpretations. You can already guess what a bunch of the other ones are going to be, right? We're going to have similar to joint consistency and inconsistency, and then we're going to have necessary truth, necessary false, and contingent, right? It's going to be the same notions as we had before. So we can say an FOL sentence is a logical truth if and only if there's no interpretation where it's false. Similarly, an FOL sentence is a contradiction if and only if there's no interpretation where it's true. Note, these are very similar to, though distinct from, the notions of a tautology and a TFL contradiction. The difference, not just the language, but the difference is in what they're defined in terms of. A tautology was defined in terms of evaluation. A logical truth is defined in terms of an interpretation. This tells us basically there's no model that's going to make the sentence false. No matter how you extend the predicates, no matter what you take the extension of the predicates to be, your sentence always comes out true. Or similarly, no matter how you fix the extensions of your predicates, sentence is always false. Yeah.
So logical truth just means tautology. If you ask me logical truth, I have to talk about sentence.
Yeah. Logical truth is always about FOL sentences, right? Tautology is always about TFL sentences.
Technically, they're the same, but when you ask me
No, technically they're very different notions. Sorry, I'm being pedantic, but that's because it's a really important pedantic point, right? This notion is always only applicable to FOL sentences, and it's defined in terms of interpretations. Tautology only ever applies to TFL sentences, and is defined in terms of valuations. But the spirit I take of what you're after is they're broadly both after the same kind of concept, right? It's giving us two different ways to talk about sentences that are always true.
the way we get there.
So the difference is basically what language they're in and how we're checking, right? So a tautology is a TFL sentence that's true in every valuation. A logical truth is an FOL sentence true in every interpretation. And a lot of times they will both be linked up to an English sentence that's just necessarily true. They're different ways to kind of come at that same basic notion we talked about way back in lecture 1. Yes?
Would you say that every tautology is a logical truth, but not every logical truth is a tautology?
It's tempting, but strictly speaking, we shouldn't really express that, because that's kind of trying to map expressions in two different languages that are structurally just not really appropriate. A better idea is that every logical truth is going to be a necessary truth. Every tautology is also a necessary truth. Whether they correspond to similar English sentences, that's beyond the scope of the language. Right? So they're all kind of in the necessary truth box, but they don't play with each other. Right? Yes?
So contradictions on the same word will be used for
Yeah. Yeah.
asking the main terms what is contradiction. I can give both.
It'll say contradiction in TFL or in FOL. Right? So I'll always make that clear. Yeah. Very unhelpful to use the same word, but thanks, Tim. That was directed at him, not anybody at the back row. Okay, so again, we have these notions of testing for validity, defined in terms of interpretation. We have our surrogates for necessary truth and necessary falsehood, right? The next one, right? Joint consistency and jointly inconsistent. We'll say that some sentences are jointly consistent if and only if there's an interpretation where they're all true, right? And they're going to be jointly inconsistent if and only if there is no interpretation where they're all true, right? That is, again, they're consistent if there's some way we can fix the extensions of the predicates that will make all the sentences true. And they're inconsistent if no matter how hard we try, we cannot fix the extensions to make all of these sentences true. So what's really cool is that we can use interpretations to test for some of these properties. To show that A is not a logical truth, some sentence A is not a logical truth, it's easy. You build an interpretation where it's false. Right? Similarly, to show that a sentence is not a contradiction, it's easy. You build an interpretation where it's true. Right? We can construct interpretations to show what we're after. Right? We specify a domain, we fix the denotation of any relevant names, and then we stipulate the extensions of the associated predicates. So this is something I think it's a little easier to see after you get an example. So here's an example FOL sentence, right? So let's show that this is not a logical truth and not a contradiction. We're going to show both of these things. We're going to give two different interpretations. To show that it's not a logical truth, we give an interpretation where it's false. So here's my interpretation. My domain is Robin Hood, the best Robin Hood, by the way. Right? If you haven't seen this Disney version, just leave and go watch it. Right? So Robin and Fantastic Mr. Fox, also a good movie, not as good as Robin Hood. That's fine. Right? Let's have the predicate F have the extension of is a fox. So in this case, it applies to Robin and to Mr. Fox. Right? And we'll have the name A be Robin and the name B be Mr. Fox. Right? On this interpretation, the sentence is false. Right? And it is false because no matter who we plug in for X, they will make the antecedent true, but the consequent is always false on the way that we've set things up. Right? Now, does everyone see why on this interpretation the existential is false? Right? So again, we check it by plugging in the objects in for X, then seeing what does that do for the sentence in the brackets, right? If we plug in Fantastic Mr. Fox, well, F Fox is true, antecedent's true, but the consequent is false because they're not the same. And then if we plug in Robin, antecedent's true, consequent's false. So no matter who we plug in, we cannot make this sentence true. So there's no way to make this sentence true. Right? The existential is false. Cool.
Does that make
No, because to be a contradiction, it needs to be false on every interpretation. That is, there's no way to make it true. Yeah, no, good. It's okay. That's why we're here, right? So the task is to show first this sentence is not a logical truth. So we want to make this give an interpretation that makes the sentence false, right? And our interpretation goes like this: we set a domain, we set the extension of predicates, and we figure out what names are picking out what from the domain. Right? So in this case, given my domain and the extension of f, right, everything in the domain is an f. So no matter who we pick, they are going to make the antecedent true. Right? But also, because of how we've assigned the names, this consequent is always false. So no matter who we plug in, they make the antecedent true and the consequent false. And what does that then do for our conditional? It's always false. It's always false, right? True antecedent, false consequent means false conditional. So no matter who we plug in, the conditional is always false. So that means it is not the case there is someone that makes this sentence true. We've set the interpretation up in such a way that the sentence is false. Cool. Yes?
Is it because f extends that doesn't make it a contradiction?
You got me for the next one, right? So, right, all we've shown is that it's possible to make this false. Let's think about showing it's not a contradiction, right? If we want to show it's not a contradiction, right, what we need to show is that there's at least one interpretation where this sentence is true. And here's one such interpretation. My domain is just Robin. Again, the best Robin Hood, right? Predicate remains the same. The extension is whatever is a fox. In this case, it's just Robin, right? And I have A pick out Robin and B pick out Robin. Right? So in this case, the one thing in our domain, when we plug it in for X, F Robin is true, and A equals B is also true. So there's at least one thing that makes this sentence true, the sentence in the brackets true, which means our existential is true. There's something that makes the conditional true, the one thing in my domain. So we've got an interpretation that makes it true, which proves this sentence is not a contradiction. It's possible to make it true, and to go back a slide, it's possible to make it false. Right? It is not a logical truth. So to go back again, right? Remember, to be a logical truth, you have to be true on every possible interpretation. Right? To be a logical truth, you need to be true on every interpretation, right? To be a contradiction, you need to be false in every interpretation. So to show a sentence is not a logical truth, just give me one interpretation where it's false. To show that a sentence is not a contradiction, just give me one interpretation where it's true. So we've got a whole bunch of hands. We'll start over here. Yeah.
Okay, so if I'm doing an interpretation, I just mess with the domain and give whatever domain I want.
You can give whatever domain you want, and you can fix the extension, the predicates however you want, and you can make the names pick out from the stuff in the domain whatever you want. That's the beauty, man. That's the beauty, right? That's the coolest thing. And literally, this is what we're doing when we're building interpretations. Set domain, set extensions, fix the names, boom. To be a logical truth is really hard because it has to then be true no matter how we do that. Similarly, to be a contradiction is really hard because you've got to be false no matter how we do that. Yeah.
Like, if you could just change the like all of that around and stuff, like how come it's not like set in stone? Like how come those two can be compared like under the same like conditions? Kind of like why are they two different? Like when you change B, why doesn't it make it a completely different like interpretation? Oh, it isn't. Oh yeah.
It's a different interpretation, sure. That's perfectly fine. Remember, everything when we talk about true or false, it's true or false according to a given interpretation. But these semantic properties, these are ones about every interpretation.
Are we supposed to take every interpretation into account?
We'll come back to that. Note, what I said here is I said you can use this stuff to test for some properties. So you can show that a sentence is not a logical truth. You can show that a sentence is not a contradiction. We're going to come back to what happens to show that a sentence is. Just between friends, and this spoils the very end of the lecture, we can't do it with interpretations. That's what we're going to do in the second half of the class. Okay, are we good so far? I realize this is a lot of stuff, but I want to finish the last little bits here, right? So we can use interpretations to show sentences aren't logical truths and aren't contradictions. We can also show that two sentences are not logically equivalent. And to show that two sentences are not logically equivalent, we find an interpretation where they differ in truth value. So for example, here's two sentences. We have this universally quantified disjunction. We have the existentially quantified disjunction. If we want to show they're not equivalent, we come up with at least one interpretation where one is true and the other is false. So here's an easy one. Our domain can be Jake and Robin. And we have the predicate extension of the extension of the predicate F be Robin, and the extension of the predicate G be empty. Do we remember what it means to say empty? Nothing in the domain satisfies the predicate. Right? If we do it this way, right, our existential is true. There's something that's an F or a G. Right? It's Robin. Robin's in the extension of F, even though he's not a G. But it's not the case that everything is an F or a G, because Jake is not an F or a G. He's not an F, and he's not a G. So these two sentences are not equivalent, because on this interpretation, the existential's true, and the universal's false. So again, all we have to do is find one. Find one interpretation where our sentences differ in truth value. And the last thing we can use interpretations to test for, weirdly, is we can show arguments are invalid. That is, if you're given an argument in FOL, you can use interpretations to show that it is not valid. And you do that by giving me an interpretation where the premises are true and the conclusion's false. So here's a very silly one, right? We have this premise and this conclusion. They look so close, and yet they are different, because it's possible to make the premise true while leaving the conclusion false. So here's an interpretation that makes the premise true and the conclusion false. We have Jake and Robin. The extension of F is Robin, and A names Jake. So on this interpretation, our conclusion is false. And it's false because the antecedent is true. There's at least one thing in the domain that's an F. But the consequent is false. A is not an F. So this conditional is false. So conclusion's false. Premise is true. Because we can pick one thing to plug in for X that will make this conditional true. Who do we plug in? Well, in this case, if we plug in Jake. If we plug in Jake, Jake makes the antecedent false. And if Jake makes the antecedent false, then what's the truth value of the conditional? It's true. So there's at least one thing that makes this conditional true, namely Jake. So premise is true, conclusion's false, argument is invalid. So here's the kind of thing I'm going to ask you, right? I'm going to give you some sentences in FOL, and I'm going to ask you to use interpretations to show me, first, that this sentence is not a logical truth, that this sentence is not a contradiction, that two sentences are not logically equivalent, and that this argument is invalid. Because these are the things you can actually do with interpretations. You can show that these properties do not hold. Weirdly, you cannot show that the properties do hold with interpretations. And that's because to do that, you have to be able to think about every possible interpretation. And that's just not something we know how to do. So, we can also build diagrammatic interpretations. I feel like that's fairly straightforward, right? We did this already if you think about the cases with Ron, Harry, and Hermione. For every person, there's someone that they love. Doesn't mean that there's some person that everyone loves. Diagrammatic interpretations do the same thing as these written out interpretations. So, our last little bit. An interesting upshot. If some interpretations make all of A1 through AN true and C false, then we know that the corresponding FOL argument's invalid. We know that the logical entailment relation doesn't hold. And we also know that A1 through AN and not C are consistent. That's what the interpretation shows us. An interpretation that refutes a claim is called a countermodel. Everything I'm going to ask you to do with interpretations will be generating countermodels. Some practical suggestions for generating interpretations. We'll talk more about these in the tutorials. But first, keep your domain small. 1, 2, 3 objects, right? Because then it's really easy to tell what the predicates are true of. It's also easy to test all the quantifications. Second, remember you can directly and indirectly stipulate extensions of predicates. Third, remember that the extensions of predicates can be some, all, or none of the things in your domain. Empty predicates are your friends. They make this stuff so much easier. And if you're dealing with two-place relational predicates, think about drawing a diagram. Some people find that much easier. I know I do, but some other people do too. Okay. So again, I'm going to construct interpretations to generate countermodels. And that's because, well, there's a lot of these properties that we've defined that we can't test. To show that a sentence is a logical truth or that it is a contradiction, we need to think about all possible interpretations. The same thing for showing that two sentences are equivalent, that some sentences are jointly inconsistent, that the logical entailment relation holds, or that an argument is in fact valid. We can't do this with interpretations because this would be a super task. Does everyone know what I mean when I say a super task, right? Finite, infinite number of steps undertaken in a finite amount of time. Good luck with it, right? Give me only interpretations. So again, just a quick table to show you what we need. What are we going to do with these ones? The ones that talk about all interpretations? Well, we can't use interpretations to do this. We can't consider all possible interpretations. We cannot simply construct a bunch of interpretations because we'd have to produce an infinite amount of them. So the best thing we can do right now is consider arguments in English. So here's a sample to show you that an argument is valid. If we know that there's something that's an F and a G, there must be something that's a G. Well, cool. So if the premise is true, there must be an object. Let's call it, I don't know, Steve, right? Steve is an F and a G. Well, if Steve is an F and a G, then that means Steve's in the domain. And we know that Steve is both F and G because, well, this is a conjunction. So that must mean that Steve is a G. And since Steve is in the domain, that means there's something in the domain that's a G. Cool. Hence the argument's valid. Now this is a very quick and dirty version, right, in English. What we're going to do in the second half of the class is formalize this. We're going to give you the machinery to actually do all of this stuff. And it's going to be natural deduction. So we're going to start constructing formal proofs. So that's going to be what we're going to do in the second half. Once we have the natural deduction machinery, together with the stuff we've talked about here, we will have our complete logical system. But importantly, all we have to do for this, right, for the midterm, is the stuff we've covered now. So, nicely done, guys. We're doing well. We're going to talk about interpretations in the coming tutorial, right? That's what we're going to do. That's the assignment for this week. Notably, no reading next week. Come with questions, come with preparedness. I will upload a practice midterm probably Thursday at some point. And that's what we'll work on the tutorials next week. So take care. See you guys all soon. Have a lovely rest of the day.